Hello everyone, welcome to my presentation. My name is Yukka from Communication System Group in the Department of Electrical Engineering at Chalmers University of Technology in Sweden. I'm very glad to attend ICC 2022. I will introduce our paper. The topic is Iterated Posterior Linearization PMB Filter for 5G Slime. Our co-authors are either from Chalmers University of Technology in Sweden or Tampere University in Finland. And here, I would also like to thank the Wallenberg AI Autonomous Systems and Software program to support my work. This is a picture from downtown Singapore that suppose we have a base station with many antennas on the top of this building. This is a user equipment here, also with many antennas. This is a signal sent from base station to the user. These signals can go over the complex propagation environment. As you can see, they can bounce by the object and generate multi-paths. And the question we want to answer is the following. Suppose one base station can send signals to the user. Can the user determine its position and synchronize with the base station and perhaps find additional information like its orientations? And can we also provide radar-like maps of the environment? So we want to solve this downlink mapping and positioning problem with 5G technologies. The picture on the right is the same as the one we had in the downtown Singapore, but more mathematical. Here we have a base station and we already know where it is. Here we have a vehicle with unknown position, unknown heading, and clock bias. The signal sent from base station to the user could be the live site, as shown in this green line. Those signals could also be bounced in the environment. For example, the signals can be bounced by some surfaces like a wall and then reach the user. But the things when the user moves, where the signal hits the wall also moves. So we parameter the surface with so-called virtual angle, which is the reflection of the base station with respect to the surface. It is fixed. So when the user is moving, even though the incident point is moving, the virtual angle is static. This is what signal looks like at the user side. This is a typical millimeter wave observation model in the literature. This PK is a sent signal by the base station, and each channel is described by a channel gain, a response vector at the receiver side, which is dependent on the angles of arrival, and the response vector as a transmitter, which is dependent on the angles of departure and the delay. At the receiver side, you can have this kind of commander, which basically makes the receiver listen to a certain direction. Given the observation variety and the knowledge of the send signal and the commander, the channel estimator can recover the geometric information, like those delays, angles of arrival, and angles of departure. Given those angles and delays, we then need to figure out what is the vehicle state and also map the environment. Here we have a challenge in the problem that is a high linearity of the model. The SLAM problem usually requires solving the joint posterior identity of the UE states and the landmarks, given the initial states and the observation. However, the models considered in the SLAM problem are usually nonlinear. Due to the nonlinearity of the model, the posterior PDF cannot be calculated analytically, so the approximations must be used in practice. The nonlinearity can be propagated by using particles, for example, using particle filter or sigma point, for example, using Kubitrov common filter, but the complexity is relatively high, because a lot of particles or sigma points will be used. The nonlinearity can also be approximated by utilizing first-order Taylor series, for example, using the extended common filter, which is equivalent to linearize at the prior mean. However, this kind of method usually performs poorly, especially the measurement noise is very low. In this paper, we studied the linearization problem of the nonlinear measurement model. Then I will explain the linearization of the measurement model in a more mathematical way. For example, we consider a measurement model. Z is equal to h of x plus n. This Z is the measurement, and this h of x is a nonlinear measurement function, and n is a zero mean Gaussian measurement noise with covariance matrix R. Mathematically, to linearize the nonlinear function hs is to approximate hs by a linear function. Like we can approximate hs with h multiplied with s plus b plus a. And this h denotes the linearized matrix, and this b denotes the Bs vector. This e denotes the zero mean Gaussian distributed variable with covariance matrix omega, which is independent of x, and also the measurement noise. Once the linearization is performed, the measurement can be approximated by the Gaussian distribution, with mean here and the covariance matrix as omega plus r. If we also know the prior, and then we can calculate the posterior mean and covariance using these two equations, and where this k is common gain can be calculated by using this equation. In Bayesian framework, the extended common filter is an usually used algorithm to handle the nonlinear measurement model. In the EKF, h of x is linearized by the first-order Taylor series, and it is linearized at the prior mean with omega equals 0, and the H matrix denotes the Jacobian of h of x evaluated at the prior mean. However, measurement is not used in the linearization, and it has some problems. For example, performance may be very bad in some cases, especially for nonlinear measurement functions with relatively low measurement noise. To obtain a better approximation, the linearization should be done with respect to the posterior rather than at the prior mean. The main reason is that the posterior PDF is always narrower than the prior PDF, especially if the measurement noise is very low. Here is an example of the nonlinear measurement function and its linearization at the prior mean and with respect to the posterior. The length of linearization is represented for the 95% confidence interval of the PDF. And the measurement function is set as the quadratic function, where the covariance of the measurement noise is set to 0.1. The prior follows a Gaussian distribution with mean 3 and variance as 4, and we analyze the case where the measurement is 0.5. In this figure, it is obvious that the linearization with respect to the posterior PDF provides better approximations and less uncertainty, as the linearization is more closer to the measurement function in the 95% confidence interval, and the 95% confidence interval is much shorter. Then we have a conclusion that the linearization should be done with respect to the posterior, but it seems problematic, as we would need to know the posterior to approximate the posterior. However, the posterior is not available. So what we do is to use the iterated posterior linearization filter to iteratively approximate the linearization parameters HB omega by solving the optimization problem. To solve the optimization problem, we can perform the optimization problem with respect to the iterative optimization of the posterior PDF, starting from the prior PDF. After each iteration, we obtain an improved approximation to the posterior PDF, from which we can obtain an improved iterative linearization. And in this optimization problem, we need to take the expectations, which can be done by using the sigma point principles. This is a summary of the iterated posterior linearization filter. We input the prior mean and the covariance. We firstly factorize the covariance P and then compute the curvature points and propagate the curvature point. And based on those points, we will approximate the innovation covariance, and the cost covariance. Then we compute the linearization parameters and use these parameters to update the mean and the covariance. And then we repeat these steps until converge. And that is so-called iterated posterior linearization filter. And it can be used to replace the extended common filter update step in many applications. For example, in our SLAM work, we replace the extended common filter update part with the iterated posterior linearization filter update part. And we compare the result and we evaluate how the implementation of the iterated posterior linearization filter affects the performance. And more details about the SLAM filter can be found in our paper. This figure shows our simulation environment. There is a base station as the triangle here, and we have 4 different surfaces with the vector angles as these 4 blue stars, and we have 4 scatter points as the red stars here. And the vehicle drives around the base station with a constant turn rate. The transmitter and the receiver are both implemented with an 8x8 antenna array, and more details about the parameter settings can be found in our paper. Then we move into the numerical evaluation of the results. We use the so-called Gauss-Bar distance to evaluate the mapping results, which is a distance that considers all the estimation error and misdetections and false alarm. We also evaluate the RMSE and the standard deviation for the positioning performance, and we compare 12 algorithms, the EK-PMB SLAM filter and the IPL-PMB SLAM filter. We firstly studied the mapping result. We could observe that the IPL-PMB SLAM filter provides better mapping results, as those solid lines are lower in both figures, which is because it has a better linearization every time step. And then we also studied the positioning result. We could also say that the IPL-PMB SLAM filter provides more accurate and precise result, as the RMSE and standard deviations on each dimensions are lower. We also analyzed the execution time on 2 algorithms. We observed that the proposed IPL PMB SLAM filter takes longer time in update step, as the linearization is done iteratively and the sigma points are used to approximate the expectations every time step. But still, the real-time operation of the filter can be guaranteed. Here comes our conclusions. Firstly, the proposed IPL PMB SLAM filter is the same as the EK PMB SLAM filter that can map the environment and estimate the UE state simultaneously. And then the implementation of the posterior linearization can help the PMB SLAM filter acquire more accurate estimates. And also the proposed IPL PMB SLAM filter also provides more precise result. And finally, even though additional computational cost is needed to obtain such performance gain, online or real-time operation of the filter could still be guaranteed. Thanks for listening. Any questions?